Hello everyone, this is Gaurav Mishra and you are watching GM Physics and I welcome you all. All right, so let's have a quick look at the topics that we'll cover in this video lecture. So the first one is concept of projection of a vector. We'll try to understand what is a projection and how it is related with vectors. Then after understanding that, we'll understand resolution of a vector in 2 dimensions. It is very much related with the previous topic, that is concept of projection of a vector. Once we understand the significance of projection in vectors, that vectors follow the law of projection, we'll also understand the physical interpretation of this resolution of a vector in 2 dimensions. Why do we resolve a vector in 2 dimensions or 3 dimensions? Here in this lecture, we will discuss only about resolution of a vector in 2 dimensions or in a plane, not in 3 dimensions. That we'll do in the next lectures. Then we'll study about parallel shifting of a vector. It is one of the properties of a vectors which is very important and that is used almost in every problem unknowingly. Parallel shifting of a vector. That vector can be shifted from one place to another anywhere in the space, provided you keep it parallel to its initial orientation. You don't change the orientation. Now, why do we do that and how can we do that? Means what justifies parallel shifting? These both things we'll understand. And finally, interconversion between polar form and rectangular coordinate form. So in the last lecture, we had discussed about various methods of representing a vector, like symbolic representation, then polar form representation, then rectangular coordinate form representation. So in this video lecture, we'll understand interconversion between these 2 important forms of representation. One is polar form and rectangular coordinate form. Means if polar form is given, you should be able to convert it into rectangular coordinate form. And if rectangular coordinate form is given and it is required, then you can convert it to polar form. All right, so first of all, let's look at a very basic concept, that is projection. What is projection? So the literal meaning of projection is, here I have written, presentation of an image on a surface. Means you obtain an image of something or some object on a screen. The device called projector does the same thing. It presents an image of something on a screen, right? So let's try to project. Let's try to obtain an image of a line on another line or a surface. So for that purpose, I have taken an arrow, a real arrow, or a stick you can consider, right? And this black one is a surface or a line. And we are trying to obtain an image of this arrow, this one, on this surface, right? So let's switch on the light in a direction perpendicular to the surface. You have to consider this light ray moving perpendicular to the surface, right? Making angle 90 degrees, okay? And now we are going to see how the image of this arrow will be formed on the surface. So you know, when light ray moves, if you keep any opaque object in its path, its image is formed, right? So this image will be formed at this point. This one will be formed here. This one will be formed here. Similarly, in this way, you find that the tail of this arrow, the image of that will be formed here. So let's call the tail's image as A and head's image as B. So the entire image of this arrow will be formed between these 2 points A, B. And this will be the image length. AB will be the image length, right? So suppose this is L. So the image obtained AB will be smaller than L. AB will be smaller than L, right? As you change the orientation of the arrow, means you go on decreasing the angle between the surface and this line, the image length will go on increasing. You can see here. Imagine again the light is moving perpendicular to the surface and we are trying to obtain image for the same arrow in different orientation. In the first case, the image will be for the head, the image will be formed here and the tail is here. Let's call it B. So AB, the image will be obtained between AB. The image length will be AB for case 1, for the first orientation. For the second orientation, the image will be formed between A and let's call this point as C. You see, I am drawing the line perpendicular to the surface. So the image will be formed in the same path, in the direction in which the light ray is traveling. This much you already know from your 9th and 10th standard. I hope you understand this much. Here we are not using a very in-depth concept of light and image formation. We are simply trying to understand projection and relate it with the concept of resolution of a vector or components of a vector. So try to understand from that perspective. So now light ray is traveling in the straight line perpendicular to the ray. So in the third one, the image will be formed between A and let's call this D. So you see, as the ray is moving parallel, means it is moving towards the horizontal surface, it is moving towards becoming parallel to the surface, the image length goes on increasing. And in the extreme case, when the ray becomes, when the arrow becomes completely parallel to the surface, in this case, this one, light rays traveling like this. Wherever we are talking about projection, you have to consider that the surface on which we are obtaining the image, the light ray is perpendicular to that surface on which you are projecting the object. The light rays perpendicular to the surface on which you are projecting the object. So this is the surface, and light rays perpendicular to it, right? And in this case, the arrow is parallel to the surface. Tail's image will be formed here and head's image will be formed here, and all the points on the arrow between A and B, they will be formed between A and B itself. So the image length will be this much, exactly equal to the length of the arrow. So you see, in this case, when the arrow is parallel to the surface, the image length and the arrow length is equal. In other cases, you see the image length goes on decreasing. In the third case, the image length is maximum out of this 1, 2, 3. Here it has decreased slightly. From AD it becomes AC, and in case 1 it becomes AB, the smallest. Now let's see in this case, the last one, this one, when the arrow is perpendicular to the surface, here theta 1, let's call this theta 1. In this case, it is theta 2. In third case, it is theta 3. You see, theta 3 is greater than theta 2 is greater than theta 1. So where the angle is maximum, theta 3, the image length is least. And where the angle is least, that is theta is equal to 0, the image length is maximum, equal to the length of the arrow. Here in this case, the angle is 90 degrees. If you project this arrow onto this surface, the black one, what you are going to get? You are going to get nothing. A point will be formed at this point. A point will be formed. There will be no length, no breadth. Mathematically, a point means no length, no breadth, no width, nothing, right? So in this case, the image length will be 0. It means the projection in this case will be 0 when the arrow is oriented at an angle of 90 degrees. Here, the image length will be equal to the arrow length. And in all other cases, there will be some finite length of the image, but the length of the image will go on decreasing as you increase the angle between the arrow and the surface. The maximum angle being 90° and the least angle being 0°. All right, so let's try to use the concept of projection with vectors. In fact, this law of projection is very much related with vectors. Vectors follow the law of projection. Let's see this through this very simple example, which I think most of us have experienced in our life. I have shown 4 cases, 1, 2, 3, and 4. A person is climbing on surfaces inclined at different angles with the ground surface. In the first one, it is 90°, means it's a vertical wall. In the second one, it is inclined at some angle, let's say 60°. In the third case, it is inclined at even a smaller angle, let's say 30°. In the fourth case, the surface has become parallel to the ground. So theta is 0° in this case. So you know from your own experience, it's out of these 4 cases, it is toughest to walk or climb on the vertical wall, and it's easiest to move on a horizontal surface. You don't feel any pull when you are standing on a ground surface. You don't slide on the surface, you are standing comfortably. You don't feel any pull or push on your body. But on a vertical wall, you need support of something, then only you can climb on it. Why is it so? You already know. Earth is pulling it in vertically downward direction. So it is hard to go against that force. So you need some support so that you pull it and then you go against the force of gravity. What happened in case 2 and case 3? What is happening here? The force is acting in vertically downward direction. In case number 2, you can see from the expression that it is easier to walk on this surface as compared to the first one. It's not only from the expression, from your own experience, you understand, or if you have not done it, you can relate that yes, on this surface, it is easier to walk. In the third case, it has become even more inclined towards the ground surface. So out of these 3, in case number 3, it is easier than case number 1 and case number 2. So what is happening in this case number 2 and case number 3 and case number 4, that it goes on becoming easier. But in the first case, it is the toughest. All right, so what is happening in case number 2 and case number 3? Why is it easier to move in case number 3 as compared to case number 2? Why is it easier to move in case number 4 as compared to case number 3? In case number 2 and case number 3 also, there is a pulling force. There is some force acting on this person. That's why he needs the support of this rope. Then only he can walk on this surface. Here also, you have to assume that all surfaces are smooth and frictionless. In this case also, there is some force acting on this person. His one hand is free, and with one hand he can walk. Means he needs the pull of one hand only at a time. Then he catches with the other hand and pulls it. Then catches with the other hand, pulls it, and does it like this, right? I have just tried to show you that in case number 3, it is easier to walk as compared to case number 2. So one hand is free. In case number 4, there is no push or pull. So drawing it, and you can mark a cross here. It shows there is no push or pull force in case number 4. Now let's try to understand it using the concept of projection. In all these 4 cases, the same force on the same person is acting, that is gravitational force. So this is something which you have already studied in your 9th class. So in case number 1, I show that the force is acting in vertically downward direction, right? And let's represent it with the help of an arrow. We have read it that we represent a vector quantity using an arrow. Here the vector quantity is force, that is gravitational force. In case number 2 also, the vector quantity force is acting in vertically downward direction. I'll represent with the same length arrow because the force is same, it's the same person. Here also the same force. Here also the same force. But why the pull is lesser in case number 2, even lesser in 3, and it becomes 0 in case number 4? Law of projection. Look here. In case number 1, assume this is the surface. I have drawn parallel to this surface and project it on the surface, this force. So you get the same length arrow, means same force is acting. That is total force, net total force is acting on this person in case number 1. In case number 2, if you try to see, so the surface is somewhat inclined. I am trying to make as much parallel as I can do. So this is the surface. Let's project it on this surface. So it is of this much length, this much. This is the amount of force that is acting. In the first case, this is the amount. This is longer, right? This is longer. In this case, it is smaller. Now the surface has become even more inclined. So let's try to make it as much parallel as we can. Now see, the component has become even smaller, right? In component means projection. Let's try to see the projection in case number 3. So in case number 3, you get the image length is smaller, or you get the projection is smaller as compared to case number 2. In case number 4, if you see, the surface is parallel to the ground. It is making angle 90 degree. If you project this arrow on this surface, you get a point, means 0. So in this case, there is no force. In this case, there is some force. In this case, there is slightly bigger force. In this case, the maximum force. So this difficulty is only because of the law of projection. In case number 1, maximum force is acting. In case number 2, slightly smaller force is acting because the projection is smaller as compared to case number 1. In case number 3, the projection is even smaller as compared to case number 2. And in case number 4, the projection becomes 0. So vectors follow the law of projection. Though we have seen it for force, it's not only limited to force, it's everywhere. All vector quantities follow the law of projection, whether it is displacement, velocity, acceleration, force, torque, angular velocity, whatever you name it, they follow the law of projection. Now we are going to look at resolution of vector using the same concept of law of projection. All right, so resolution of a vector in 2D or plane. So here we will restrict our discussion to resolving a vector in 2 dimension or a plane only, not in 3 dimension. That we'll do in the next lectures. So resolution of a vector in 2D or plane. Resolution of a vector simply means you find or you project a vector along different axes, x and y, of a Cartesian plane or a rectangular coordinate plane or simply an xy plane. So a vector quantity, it can be anything, force, displacement, velocity, etc. Whatever it be, we represent it with an arrow. So let's call this as a vector. So I have represented a vector with an arrow. So we have to project this arrow along x-axis. Means we have to find its image along x-axis and along y-axis. This is what we call resolution of a vector. So let's see. This is my a vector and its magnitude is represented by its length. So let's write the magnitude of the vector, means mod of a vector, or simply a. A means magnitude of the vector. So the length of the vector is equal to A. And suppose it is inclined at an angle theta with respect to x-axis. We always measure angle with respect to x-axis. Anti-clockwise is positive, clockwise is negative. We have already discussed about the sign convention, right? So how do we project? So what we do is we draw a line perpendicular to x-axis, right? So from O to A will be the projection of this vector along x-axis. Let's call this is equal to AX, right? Similarly, put a perpendicular from the head of the arrow on y-axis. So from O to B, this will be the projection of the vector along y-axis, and let's call this AY. AX means projection along x-axis, AY means projection along y-axis. So this AX and AY are called the components of the vector. So this projection of the vector is in fact called the components of the vector. So the components of this vector A, that is A vector, is AX and AY along x-axis and y-axis respectively. For simplicity, I have taken the vector in first quadrant. It can be in any quadrants. This should be clear. So now see, our purpose is to find the value of AX and AY. Then we will be able to resolve this vector, or we'll be able to find the components of the vector. So we always find the projection along two mutually perpendicular lines. One is x-axis and one is y-axis. These are called the components of the vector, and this method is called resolution of a vector. So let's find out. First of all, I am going to find the value of AX. Let's find AX, right? So see, AX is in fact the base of this right angle triangle. Which right angle triangle? OA, and let's call this as P. Let's call this P. OAP. In the right angle triangle OAP, OA is the base and OA is AX, right? So we can use trigonometric relation to find AX. We know the value of this OP, that is the length of this arrow, which is equal to A. So I can write base and hypotenuse relation cos theta. Cos theta is equal to base upon hypotenuse. Hypotenuse is known, theta is known, AX is unknown. So we can find AX is equal to A cos theta, right? This is my X component of the vector. Proceeding in the similar manner, we can find the value of Y component, that is AY. Let's see. Now look at this right angle triangle, OPB. OPB. It is a right angle triangle with angle 90 degree at point B. Okay. We have to find AY. So let me write this angle. This total is 90, so this is 90 degree minus theta, right? So this angle is 90 degree minus theta, so this is the base. OB is the base of the right angle triangle OPB, okay? And this hypotenuse OP is already known. We have to find the base. Again, we will use that trigonometric relation, cos of this angle 90 degree minus theta. So we can write cos of 90 degree minus theta is equal to base. So base is OB, so that is AY, that is Y component of the vector. So base upon hypotenuse is A, so this is A. So you get AY is equal to A into cos of 90 degree minus theta. What is cos of 90 degree minus theta? Sin theta. So we write sin theta. So we obtained the X component and we obtained the Y component, means we have resolved the vector. See, This one is our x component, OA is the x component, and this is y component. Now I can express this vector in rectangular coordinate form in its components. Write A vector is equal to AX. This is along positive x-axis, and for positive x-axis we use I cap. For positive y-axis we use j cap. For negative x-axis minus I cap. For negative y-axis already been discussed in the previous lecture. So we can write AX along positive x-axis, so I cap, plus AY along positive y-axis, so j cap. So finally we get A cos theta I cap plus A sin theta j cap, right? So these are called the components of the vector. This is my x component and this is my y component. So for any given vector, you simply have to find its projection along these two mutually perpendicular lines, that is x-axis and y-axis. Those are called x and y components of the vector, and this method is called resolution of a vector. From the components of the vector itself, we can calculate the magnitude, we can calculate the direction, and this has been done in the previous lecture. This is also called rectangular coordinate form representation. If you remember, this is the x component AX, and this is the y component AY. If a vector is given in rectangular coordinate form representation, we know how to calculate the magnitude. If you remember, A vector mod of this magnitude is equal to root of AX square plus AY square. Square of the components, root of that. That is the magnitude, and theta can be calculated as tan theta. This theta is with respect to positive x-axis. Tan theta is P by B, AY upon AX. This we have already done in the previous lecture. You can check it from here. Tan theta is perpendicular, AY upon base, AX. You can also check it using these values. You will get tan theta on both sides. Mod of A, AX square plus AY square, AX square plus AY square. This we had obtained using Pythagoras theorem. All right, so let's look at an example of resolution of vectors. Here are two vector quantities. One is force of 100 newtons inclined at an angle of 60 degrees with respect to x-axis, and another vector quantity is velocity vector, whose magnitude is 150 meter per second and direction is 150 degree with respect to x-axis. So the question is, you have to find the components of these vector quantities in this xy plane. This is x-axis, this is y-axis, and you have to express these vector quantities, that is force vector and velocity vector, in vector form or in a component form or a rectangular coordinate form. Everything is same. So let's start with question number 1. Question number 1 is force of 100 Newton, this force vector of 100 Newton at an angle of 60 degree, with respect to x-axis. So the length of this arrow represents the magnitude of the vector. So here we can write 100 newtons, right? We have to find the component of this vector quantity. So simply from the head of the arrow, draw two perpendiculars, one on x-axis to find the x component and one on y-axis to find the y component, right? Now we don't need to write the trigonometric ratios once again. We already know that this quantity, the x component, will be a cos theta and y component will be a sin theta. A cos theta, a means 100 newtons, so 100 cos theta, here theta is 60 degree, so cos 60 degree. How much is that? So 100 into cos 60 is 1 by 2, so that is 50. That is along positive x-axis, so we can write positive I. Is that fine? So this is my x component. Now let's find y component, that is ay. This much is y component. So how much is this? A sine theta. So I can write this as a sine theta means, let me write here, y component of this vector quantity, that is force vector, can be written as a sine theta. So that is 100 into sine theta, that is 60 degree. So that is 100 into sine 60 is √3/2. So that is 50 √3. That is along positive y-axis. So here you will write positive j cap. So now we can write force vector is equal to force along x-axis, x component of the force, plus y component of the force, right? Whether you can write like this or you can write fx I cap plus fy j cap. So what is fx? That is 50i. So I'll write here 50i cap plus what is fy vector? That is 50 √3 j cap. So I'll write 50 √3 j cap. So this is my force vector. Got it? All right. Now let's look at question number 2. Question number 2 is the velocity vector, this one. And it is inclined at an angle of, this is inclined at an angle of 150 degree with respect to x-axis. It means this angle is, this total angle is 180 degree and this one is 150 degree. So this is 30 degree, right? So we have to find the x component and the y component. We have to project this vector along x-axis and y-axis. That is called resolution of a vector or finding the components of the vector. So here we are doing it for velocity vector. So simply drop perpendicular from the head of the arrow on x-axis to obtain the x component. Here you see the x component is along negative x-axis. And again, drop a perpendicular from the head of the arrow on y-axis. The y component is along positive y-axis. So first of all, I'm going to find the x component of the v vector, and let's call it vx, right? So vx is this total is 150 meter per second. So the magnitude of the vector is 150. So 150 cos 30, Vx is equal to 150 into cos 30. You can write 150 cos 150. Then you will get the sign from the trigonometric ratio itself. But here we already see that the component of the vector is along negative x-axis. So I don't need to write cos 50. I'll simply write cos 30 for convenience, and I'll put minus I cap because it is directed along negative x-axis. So here I write 150 into cos 30. Cos 30 is √3/2. So that is 75 √3. So Vx is 75 √3. So Vx vector is equal to 75 √3 minus I cap because it is along negative x-axis. Vx vector means the x component of the v vector. Vx vector means the x component of the velocity vector. Now we are going to calculate the y component of this vector quantity, that is v vector, right? So this angle is 30 degree and we have to find this y component. So again we can write Vy is equal to 150 into sine theta. What is sine theta? 150 into sine 30 degree. How much is that? 150 into 1/2. That is 75. And it is directed along positive y-axis. So we'll write j cap. So here you can write Vy vector. Again, Vy vector means the y component of the velocity vector. So that is 75 j cap. So now we can express our velocity vector V vector as Vx I cap or simply Vx vector. Vx vector plus Vy vector, right? So what is Vx vector? That is minus 75 into root 3 I cap plus Vy vector is 75 j cap. So this becomes my V vector. This is X component and this is Y component. This is what we call resolution of a vector, finding the components of the vector along X and Y axis. The components can be both X and Y components can be positive or negative. You have to see it in the quadrant. Where is it located? Whether it is in first quadrant, second quadrant, third quadrant, or fourth quadrant. And that we can understand by looking at the angles. If it is between 0 to 90 degree, it will be in first quadrant and both the components will be positive. If it is between 90 to 180 degree, it will be in the second quadrant and Y component will be positive, X component will be negative. If it is between 180 degree to 270 degree, so it will be third quadrant. Both the components X and Y will be negative. If it is 270 to 360 degree, it will be fourth quadrant. The X component will be positive and the Y component will be negative. So you have to look for that from the angle, whether it is in first quadrant, second quadrant, third quadrant, or fourth quadrant. Accordingly, you have to take the components and then you have to put the sign positive or negative. Got it? All right. There is a question. Is there any rule for the choice of axis for the resolution of a vector? Means, is there any specific rule that has to be followed for the choice of axis? Which axis to choose for the resolution of a vector? I mean, do we need to have this as x-axis and this as y-axis as usual in all problems? Is it mandatory, I mean? Or can we take like this is my x-axis and this is my y-axis? Or sometimes like this is x-axis and this is y-axis? Can we do like this? Or we have to take this as x-axis and this as y-axis in all problems? The answer is no. There is no such specific rule that has to be followed. You can choose any axis. That is completely your choice. It depends on the problem at hand and the convenience, which will be convenient for you. It's completely your choice. You can take this one as usual, or this one, or this one, or any one that you can make, that you can think of. Let's take an example. Suppose this is an inclined plane, right? The angle is theta. A force is acting in vertically downward direction on some object. I need to take the components of this force as a part of the problem. So do I need to take the components along x-axis and y-axis like this? You can, but this is not necessary. I can take this as my x-axis along the inclined plane and this as y-axis. And accordingly, I'll take the components of this force. Let's say this is the force vector. So I take the component along this x-axis. This will be my x component and this will be my y component. It's completely your choice. So in that sense, a vector has infinite components. More clearly, a vector can be resolved in infinite ways. But always it will have components along two mutually perpendicular lines. But you can do this in infinite ways, right? So the answer is there is no any such rule. You can resolve a vector in excess of your choice, and that completely depends on the problem at hand, the convenience. These things decide which coordinate axis you will choose for the resolution of a vector. All right, now parallel shifting of a vector. What it means? It means you can shift a vector parallel to itself anywhere in the space without affecting it. Means the vector remains unaffected if you shift it anywhere in the space, anywhere. Means whether you place it here or place it here or place it here or place it wherever you take, it doesn't matter. The vector doesn't change. Why is it so? What is the reason? Here we are representing a vector by an arrow. Its length represents the magnitude of the vector, and its orientation represents the direction of the vector, or the direction of the arrow represents the direction of the vector. So when you shift it parallelly, you neither change the length of the arrow, means the magnitude of the vector remains same, and since you are shifting parallelly, you are not changing the angle with respect to x-axis, or simply you are not changing its orientation. So you are not changing the direction of the vector. So you neither change the magnitude nor the direction. So the vector remains unaffected. You can place it anywhere because you are neither changing the magnitude nor direction. So wherever you keep, it doesn't matter because the magnitude and the direction remains the same. So the vector remains the same, remains unaffected. That's why we can shift vectors parallel to itself anywhere in the space. The only condition is it must be parallel to its initial orientation. That should not change. The length of the arrow should not change. The orientation should not change. Now, wherever you keep, that is completely your choice. All right. Now the question is, why do we even do this? Why are we required to use this parallel shifting of a vector? So let's try to understand this through an example. This is a block on which three forces are acting, three force vectors are acting. One is F1 vector, one is F2 vector, one is F3 vector, right? So in most of the problems, we are required to perform mathematical operations on vectors. And for that, we need to resolve these vectors into their components, right? So for that case, you'll have to resolve F1 vector into its components here. You'll resolve F2 vector into its components here. And you'll resolve F3 vector here, right? So rather than doing this, what we can do is we can arrange all these three forces at one point without changing the orientation and the length of the arrow, means without changing the magnitude and direction of the vector. So what will I do? I'll bring this F1 vector and place in this coordinate plane or XY plane. This will be my F1 vector at the same angle, 60 degrees. You don't have to change the orientation, neither the length. Similarly, F2 vector can be placed here, F2 vector, making the same angle. Let's say this is 30 degrees. And you can place F3 vector here, right? Making angle 90 degrees. Now I can resolve the components of these three vectors in the same XY plane, and I can perform mathematical operations on them conveniently. So this is one of the reasons, that is convenience. Now, second reason is some of the mathematical operations like addition of vectors. There, we are required to arrange the vectors in a particular sequence. Head, tail, head, tail, head, tail. We'll see in the coming lectures. And then we can perform the addition of the vectors easily without resolving the vectors into their components. We can perform the addition easily. Like in this case, I'll keep my F1 vector. I'm keeping it parallel. I'm not changing its orientation. I have tried to make it exactly parallel. This is F1 vector, right? I'll bring this F2 vector here, keeping at the same angle. This is my F2 vector, making 30° with the horizontal. This is making 60° with the horizontal, right? Now I'll place this third vector, F3 vector. This is F3 vector, making an angle of 90° with respect to horizontal. Now I have arranged these three forces in a particular sequence, which is required for addition of vectors. In detail, we'll study in mathematical operations of vectors, that is addition of vectors. But here I'm trying to make you understand that here parallel shifting of vectors will be required to perform the addition conveniently, right? So these are some of the reasons we are required to shift vectors parallelly, right? So this is all about parallel shifting of a vector. The conclusion is, the final conclusion is, you can shift a vector without changing its orientation. You can place it anywhere in the space. It won't affect the vector. All right, now it's interconversion between polar form and rectangular coordinate form. So if a vector is represented in polar form, we have to convert it into rectangular coordinate form. And if it is given in rectangular coordinate form, we have to convert it into polar form. That is called interconversion. So let's see. You already know that polar form representation directly shows the magnitude and direction. So suppose a vector, A vector, is given in its polar form. So from the previous lecture, you understand the polar form representation will be of this form, L theta, where L represents the magnitude and theta represents the direction of the vector. The theta is measured with respect to positive x-axis. That is the standard reference. If it is positive angle, it is in anti-clockwise with respect to x-axis. If it is negative angle, it is in clockwise with respect to positive x-axis. Rectangular coordinate form for the same vector, A vector, it will be in the form of coordinates of the head of the row. And now we understand that is the projection of vector along x-axis and y-axis. Those are the components of the vector along x and y, x components and y components. So the general form in rectangular coordinate form representation will be like this. A vector is ax I cap plus ay j cap, where ax and ay are the components of the vector or the coordinates of the head of the row, right? So how to convert polar form into rectangular coordinate form? This is the first one. In second, we'll see how to convert rectangular coordinate form into polar form. So we have to assume a vector A is given as L theta. So first of all, we'll represent it in a coordinate system. Usual, this is x-axis, this is y-axis. At an angle theta, I am drawing that vector whose magnitude is L. So length of the arrow represents the magnitude. It is L. The angle is theta, right? So what is given in the polar form representation, that is what I have shown in this rectangular coordinate system. So what we have to do is we have to take the components of this vector. We have to simply resolve and then we will obtain rectangular coordinate form. So draw perpendicular from the head of the arrow on x-axis and drop the perpendicular from the head of the arrow on y-axis. Using trigonometric ratios, which we have already done, we can write this component, that is ax, will be L cos theta, and this component, which is y component, which is also equal to this one, opposite sides of a rectangle. So this will be the y component of a vector, ay will be L sine theta. Now we can convert polar form into rectangular coordinate form. So the same vector can be written as in rectangular coordinate form as L cos theta I plus L sine theta j, or L into cos theta I plus sine theta j. This is the magnitude, this is the direction. So this is polar form to rectangular coordinate form. All right, now we are going to discuss the second interconversion, that is rectangular coordinate form to polar form. You know that in rectangular coordinate form representation, we express a vector as sum of its components along x-axis and y-axis. So the general form representation of a rectangular coordinate form is something like this. Let's take a vector as a vector as x component plus y component, axi plus ayj. In polar form, it is given like this. A vector is L theta. L is the length of the row, magnitude of the vector. Theta is the angle. We have already discussed about it. So simply, in interconversion between rectangular to polar form, means if you want to convert rectangular coordinate form to polar form, you simply have to find the magnitude of the vector and its direction with respect to x-axis, that is angle theta with respect to x. So see, first of all, I'm representing this vector in its components. Let's see, this is my y-axis and this is my x-axis. This is x-axis, this is y-axis. And let's say this is a vector, right? This is a vector. So its components are given along x-axis, means perpendicular from the head of the arrow on x-axis. So this x-axis, along x-axis, the component of the vector is given as ax. Along y-axis, the component of the vector is given as ay. So this is the representation of the vector in rectangular coordinate form, but we have to express it in polar form. Means you have to find the length of the row and its orientation, that is theta with respect to x-axis. So first of all, let's find the magnitude of the vector, that is L. So simply we have already discussed in the previous lectures, this ax is the base, ay is the perpendicular, and this is a right angle triangle. So we can use Pythagoras theorem. We can find mod of a vector, that is magnitude of the vector. Here, that is the length of the row, is equal to root of base square plus perpendicular square, or x component square plus y component square. Ax square plus ay square, root of that, it gives the hypotenuse, that is the length of the row, that is the magnitude of the vector. Now we have to find the direction, this theta with respect to positive x-axis. So we can use the trigonometric relation. Tan theta, we know the perpendicular is ay and the base is ax. The perpendicular is the y component, the base is the x component. So we can write tan theta is equal to perpendicular, that is y component, upon base, that is x component, ay upon ax. So theta is tan inverse of ay upon ax. So now we can express it in polar form. We can write the same vector, that is a vector, as L is equal to, that is magnitude of the vector, as ax square plus ay square, and theta as tan inverse ay upon ax. So this is my polar form representation from the given rectangular coordinate form representation. So this is rectangular coordinate form to polar form. All right, so let's take an example on interconversion between polar form and rectangular coordinate form. So the question is, velocity vector is given as v vector is minus 2i plus 3j. Express it in the polar form. Means the velocity vector is given in rectangular coordinate form. It is given in the form of its components. It is expressed as sum of its x and y components. And you have to express it in polar form. You have to write it in polar form, means you have to find the magnitude of the vector and its orientation with respect to positive x-axis. Okay, so let's say this is x-axis, this is y-axis, this is positive x, this is negative x, this is positive y, this is negative y, right? The components are 2 units along negative x-axis minus I cap and 3 units along positive y-axis. So let's make those components. So let's say this is 2 units. This is my x component. So this is 2 units. And let's say this is 3 units. This is y component, that is along positive y-axis. This is 3 units, right? So if we want to find the vector, so let's draw the perpendicular lines. This is the point of intersection. So this will be the head of the row. This is my vector. Assume this is a straight line. So this is my vector. Okay. So what we have to do, we have to find its length, that is magnitude, and its direction. This angle we have to find. Okay. So first of all, magnitude of the vector, that is equal to ax square plus ay square. So the x component is 2, y component is 3. So we can write root of 2 square plus 3 square. How much is that? 4 plus 9. So that is root of 13 units. Maybe it is meter per second. Let's call it meter per second. So that is root 13 meter per second. That is the magnitude of this vector, which is the velocity vector. Now we have to find the direction. So this angle we have to find. So let's proceed with finding this angle first, right? And let's call this as theta. So you see, this angle can be calculated using trigonometric ratios. In this right angle triangle, you can write tan theta is equal to perpendicular, which is 3 upon base, which is 2. You don't need to look at this triangle. You can always write y component upon x component, only magnitudes, no need to write the direction if you have expressed the vector in its proper quadrant. So first find this angle using positive y component upon positive x component. Whether it is negative or positive, don't consider, only write positive components. Then you will get this angle, not this angle, right? So here theta is tan inverse 3 by 2. It is not the angle which we are looking for. This is the angle which we are looking for from positive x-axis, this bigger angle, right? So for this, we'll have to write 180 degree, this entire angle, 180 degree minus this theta. So minus of tan inverse 3 by 2, right? So this is the required angle with respect to x-axis. So now the polar form representation can be written as v vector is equal to first the magnitude. So that is root under 13 meter per second or root under 13 units, 180 degree minus tan inverse 3 by 2. You don't need to write the exact angle. How much is tan inverse 3 by 2? If it is given in the question, then subtract it from 180 degree. If it is not given, you can write as it is. For standard angles like 30 degree, 45 degree, 37 degree, 53 degree, 60 degree, for these you can write. And for these, you don't need to write until and unless it is given in the question. You can leave it the way it is, right? So the polar form representation is root under 13 units, 180 degree minus tan inverse 3 by 2. This is the polar form representation of the velocity vector, which is given in rectangular coordinate form. All right, so this is what we had to discuss in this video lecture. Till then, keep practicing, keep learning, and keep growing. Till then, all the very best. Bye-bye.